This is on. Great. So thank you, Marco, and good morning, everyone. So yeah, I'm going to try to continue where we left off yesterday morning. Again, the goal of these lectures is to give a kind of pedagogical introduction to quantum optomechanics. What I did in the last lecture was to hopefully motivate the field for you. Why are so many people interested in this particular subfield of, let's say, quantum optics? And give you a basic flavor of the simplest kind of theory we use to describe these systems. So what I want to do in today's lecture is to actually do something with that basic theory that we built up, describe some of the simplest phenomena in quantum optomechanics. So the physics of what people call dynamical backaction, how we can use light in the cavity to control the mechanical state, in particular cool it down to close to the quantum ground state. I'll also tell you about something called optomechanically induced transparency, where we can also think about the opposite kind of effect. So even in this regime of very, very weak couplings between the mechanical motion and the photons in the cavity, the mechanics can do something dramatic to the dynamic photons in the cavity. And in particular, the way I like to think about it is the mechanics can change the cavity density of states in a useful way, in a way that's analogous to electromagnetically induced transparency in atomic systems. Okay, so that's the plan for the first half, the first part of this lecture. Hopefully we'll have time to get into the second part of the lecture. We'll actually get into understanding the physics in a more kind of quantum regime of the system, where the optomechanical coupling matters at the level of single phonons and single photons. Okay, so that's the plan, but again, questions are more than welcome. We'll see how far we actually get this morning. Okay, so just the story so far. I motivated for you this very, very basic optomechanical coupling Hamiltonian. The number of photons A dagger A in the cavity couples to the displacement of some mechanical degree of freedom, which I write in terms of phonon raising and lowering operators. This coupling is typically very, very weak. To get something, we need to strongly drive the cavity, put lots of photons in it. There's going to be a large coherent laser drive on the cavity at some frequency, omega laser. So what we do to deal with that drive, we make these displacement transformations on both the photon lowering operator and the mechanical lowering operator. The drive induces some average number of photons, that A bar squared, that's going to be very, very large. And so once we go into the rotating frame at the laser frequency, and once we make this displacement transformation, our final Hamiltonian has this form here. So now in terms of my displaced photon operators, the optomechanical coupling has both this quadratic coupling part, so this thing involving D dagger D, but then it also has this linear coupling part with just a single power of D or D dagger. And this part is the part that matters in most experiments, because this part of the interaction not only involves this very small coupling strength G, it also involves this large amplitude that we've induced in the cavity with the laser drive. Again, that alpha bar CL is something that the experimentalist can control. So in the standard regime of optomechanics relevant to most experiments, little g by itself is just irrelevant. We can drop this term. We reduce our system to something that at first glance might seem very boring. We reduce it to two coupled harmonic oscillators. We just have this linearized optomechanical interaction. Little g has become big G. And again, big G is just the product of little g and this induced amplitude in the cavity. Okay, and again, that I can think of in terms of the square root of the number of coherent photons my laser has induced in the cavity. Okay, and so the main question for the first part of this talk is, okay, given this coupling in this simple linearized regime, how does the light actually modify the properties of the mechanical resonator? How does it affect the mechanical dynamics? How does it affect the state of the mechanics, its temperature? Yeah. So the number of thermal photons, so everything I've said here is, in a sense, all the coherent physics. Even the driving of the cavity with the laser field, that's a term I could include in the coherent Hamiltonian. So to understand all the dissipative physics and the number of thermal photons or phonons, so that we also talked about last class, and that was, last lecture, sorry. that was using this formalism of quantum Langevin equations to describe the dissipative reservoirs that are driving both the photons in the cavity, so that is the light that's leaking in through this semi-transparent mirror into this mode, and the sources of mechanical dissipation. So all the information about temperature, so we have these Langevin equations here that correspond to this linearized Hamiltonian. I have the coherent dynamics. So again, delta here is the detuning of the laser from the cavity frequency. I have now damping terms for both the photons and the phonons. And corresponding to that, I have noise terms, right? This operator valued white noise. The number of thermal photons associated, or phonons, associated with the drive is just in these noise terms. It does not appear, so again, that's a good point. This N-bar cavity does not include any thermal photons that could be in the cavity. It's only coming from the coherent photons you've induced in the cavity with your drive. Well, there's no assumption like that that's needed here, right? So if everything's at thermal equilibrium, yes, they'll be at the same temperature, but so here what I've done is, in describing the sizes of these noise terms and these Langevin equations, I've expressed the temperature in a number of thermal quanta. So given the huge difference in frequencies between your photons and your phonons, typically you're going to be dealing with almost no thermal photons, and you'll be dealing with a lot of mechanical phonons, just in terms of what the baths are described by. Okay, but those show up in the noise terms here. They do not show up anywhere in the coherent Hamiltonian. Okay, so not all photons are alike. Coherent photons good, thermal photons bad. Okay, so this is the starting point. This is the question we want to go after. Okay, good. And so what I'm going to do first to sort of address this question of how are the mechanical dynamics modified is let's just actually look at this entire system semi-classically. So let's actually look at the equations of motion coming from the original Hamiltonian. Right? I could have nonlinear Langevin equations if you want. Let me get rid of all the hats, right? Then I have a system of classical nonlinear equations. What's the dynamics coming out of that? And remember, that's something that we have to deal with, even if we want to do this quantum theory. Because how did we find, or how did I tell you, to find these classical displacement values? Well, you need to solve the classical equations of motion. Okay, so here are the classical equations of motion for this optomechanical system. Okay, so I've changed notation here a little bit. So alpha now is the average value of the photon lowering operator. I'm working with mechanical position as opposed to the average of the mechanical lowering operator. You know, these things are really equivalent. The optomechanical coupling, as opposed to talking about this G, I've just written the derivative of how the cavity frequency depends on X. Okay, so this is that G naught, or that that little g I had written, divided by the size of the mechanical zero-point motion. So here, and again, we're working in a rotating frame. So here I have the cavity frequency depending on position. I have the damping of the cavity. This is the external laser drive that I'm parameterizing with this parameter alpha L. Its phase doesn't matter for what I'm talking about, so let's just set it to 0. Here's the mechanical equations of motion. The coupling now is this, again, it's coming from the full Hamiltonian here. We haven't linearized at all. So this is this radiation pressure force. There's a force on the mechanics set by the number of photons in the cavity. And this is the mechanical damping. That gamma is the same as the gamma that's sitting in that equation there. Okay, so so these are our semi-classical equations of motion. No quantum mechanics, no even classical noise in these equations. These aren't Langevin equations. So the first thing we could think about is, well, what are the solutions, the stationary solutions to these classical equations of motion? So again, we're in a rotating frame at the laser frequency. So I need to solve these equations with the derivative set to 0 to find the classical average amplitude in the cavity and to find the classical average equilibrium position of the mechanics. And again, going back to the quantum theory, that will then tell me this alpha bar, this A bar, and this B bar. Yep, sure. Well, so look, I can do my calculations any frame I want. If you then want your answer in your frame, I know how to do a unitary transformation. So look, this is just shifting what we call the zero of frequency. So it's easy to go back to the lab frame. Yeah, so there's no complexity there, yeah. So solving these equations of motion, so what do I do? Well, look, let's first set the time derivative of the mechanical oscillator to be 0. I will then find that x, the equilibrium position of the mechanics, is determined, it balances basically the force coming from the number of photons in the cavity, right? So if there are photons in the cavity, it's a force on the mechanics is displaced, that's fine. So I get some mechanical displacement, and then I plug that back into the equation of motion for the cavity field. And so now the cavity has displaced. If x has changed, that changes the frequency of the cavity. So what I end up with at the end of the day for this equation determining the steady state amplitude in the cavity is basically something we already talked about, that because of the optomechanical interaction, the cavity effectively has become nonlinear. So what this is basically telling me is the effective cavity frequency now depends on the number of photons in the cavity. Okay, so you could think of this as the equation for a Kerr cavity. So a cavity with, again, a frequency dependent, intensity dependent frequency. This is also the kind of equation of motion for a driven Duffing oscillator. Okay, so what's the subtlety here? The subtlety here is, of course, so now I want to solve this equation, right? This equation can have more than one solution. So this is the well-known bistability for a Duffing oscillator. It's the kind of optical bistability physics that was even hinted at, I think, in Jacqueline's talk. And that's an issue here. So if you pick a red detuned laser drive, so this delta is negative, if I now look at the solutions for the classical equations of motion, and I drive hard enough, 1 second, at red detunings, I have this resonance curve tilting over. I can have more than one solution. Okay, so this is what's known as the static optomechanical bistability. This was, again, something that was measured a very, very long time ago in the group of Herbert Balter. Okay, and this is actually an issue for our quantum theory. Because again, in my quantum theory, I want to linearize around the classical solutions of the equations of motion. If I have more than one, that's an issue. The good news is to actually reach this regime requires a laser drive much, 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 much stronger than anything that we're going to be talking about. Okay, so for all intents and purposes, I can ignore this physics for the rest of the talk. I thought I would be being dishonest, though, if I just said, solve the classical equations of motion, everything is fine, let's just pursue. So this is something you have to be careful of. Make sure there is a unique solution to your classical equations of motion before you go ahead and do this kind of linearized treatment. Okay, and offline, I'm happy to tell you about all sorts of papers that make the mistake of writing these equations down without worrying about this, and then nonsense ensues, right? So nonsense bad. Make sure you solve this part of the problem first. So DJ, you had a... Exactly. It doesn't show up here because here, if I'm asking for time-dependent solutions, right? If you want, I have an infinite amount of time for everything to happen. The fact that in reality, right, this nonlinearity takes time to build up, that's completely lost for the steady state. If I'm going to ask something dynamical, right, then I'm going to have to worry about that. And that we'll hopefully get to is when we really start talking about the nonlinearity and the quantum regime. Yeah, so there's, if you now ask about the frequency-dependent properties, so even the frequency-dependent scattering, you will know about the fact that this nonlinearity, if you want, it's like having a Kerr constant or a Hubbard U that has a kind of frequency dependence. So if you start probing things spectrally or asking about scattering at a given frequency, you'll start to see that. Okay, so that's kind of the static properties. We see even just for the steady state, the optomechanics does something to the mechanics. What about the dynamical properties of the mechanics? Yeah, go ahead. Yeah, so this is open up Landau and Lifshitz or your favorite classical mechanics textbook. You know, you have a bifurcation basically in terms of the intensity, right? When do you actually get one real solution or when do you get three real solutions? So that's this bifurcation here. If I look at this point here, right, where it seems like I have multiple solutions, right? One of those solutions is unstable, two are stable. So this is really, really well known. It's a very basics kind of nonlinear physics. Okay? And a way of thinking about it is if I'm really strongly red detuned, you would imagine that, okay, even if I drive, I'm not going to get much amplitude at all. But now you have this funny thing that if I'm strongly red detuned, delta is negative. If I happen to have a lot of photons in the cavity, the effective detuning becomes 0. Right? So that kind of self-consistency can give you this other solution, this upper branch, where you have a lot of photons in the cavity, despite seemingly have a very big detuning. Right? Yeah, so as you approach this unstable regime, so before this resonance curve tilts over, and you use this kind of formalism, you would find an instability, right? So in terms of I could think of a dynamical matrix as describing this set of linear equations. I could look at its eigenvalues. I would find that as I approach this regime, one of my eigenvalues becomes undamped, right? And when I go beyond that, I find that there's exponential growth, right? So the linearized theory also tells you something is going wrong, right? So once I push beyond that, I need to do something a little bit different, right? I need to really worry about the fact that there's more than one classical steady state. So are you worried about mechanical modes, or are you worried about photonic modes? So so again, the question is always system dependent. In the vast majority of optomechanical systems, it's a really good approximation. So I talked last time, I really kind of focused on a kind of Fabry-Perot cavity. So the fact that, first of all, the modes are high Q, right? So the line width of each mode is much, much smaller than the free spectral range. And then on top of that, free spectral range is much, 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 much bigger than the mechanical frequency. So the idea of just focusing on a single optical mode, talking to your mechanical resonance, and not worrying about the fact that maybe the mechanics could actually couple different optical modes, that's a great approximation. So now it turns out there are regimes where you'd love to have more than one optical mode. Okay, so then there are clever experimental setups where you specifically go out of your way to have two modes, two photonic modes, that can resonantly talk with the mechanical mode. Okay, so the short answer is you normally have to do some work as an experimentalist to actually get more than two modes to be at play. That's doable. That leads to new, interesting physics and interesting possibilities, and I do hope to get to that. Okay, so let's make things move. Let's think about dynamics, right? So how are the properties of the mechanical resonator actually changed? And so what we want to do at the end of the day is we want to calculate a Green's function, right? But when you calculate a Green's function, if you're not careful, you can get the impression that you're doing something quantum when you're not, right? So let's calculate a Green's function classically, right? We're just going to calculate, starting with these classical equations of motion, we found the steady state. Imagine now I drive the mechanical resonator. I add a term to this second equation. It's just a tiny external driving force on the mechanical mode. Right? So if I add a tiny, tiny, tiny driving force in the mechanical mode, I assume that linear response is going to work. I'm going to get a tiny amount of induced motion in the mechanics. And I want to basically find the susceptibility that describes, given the driving force I've added, how much induced motion do I get? Okay, and so the way I would do that, that's sort of standard. I have these stationary solutions I've found. I'm going to consider small deviations from those stationary equilibrium values, and I'm basically going to linearize these equations to find how this delta alpha and this delta x respond to this small external force. And the thing that I care about at the end of the day is how the mechanical mode basically responds. So I can do that, in this completely classical way from these equations of motion. There's no quantum mechanics there at all. I could also do that using these Langevin equations. So these linearized Langevin equations, so here they are written again. I could basically solve these by Fourier transforming. So here I've called V the vector of these operators, N the vector of these kind of source fields, these noises. When you solve these equations in Fourier space, there's some susceptibility matrix, right? The elements of that susceptibility matrix are basically what you would call a retarded Green's function. But again, all of this is classical, no matter what you choose to call this. Sure. Okay, so at the end of the day, what is this Green's function going to look like? So my mechanical Small induced mechanical motion is proportional to the external force. Here is my mechanical susceptibility. The frequency of the mechanics, it's damping. Okay, now little gamma has become big gamma. I apologize. And all of the effects of the optomechanical interaction are lumped in this thing sigma that is basically the self-energy of the mechanical resonator coming from this linearized optomechanical interaction. So this self-energy is going to be second order in the many photon optomechanical interaction, big G. And the idea is, okay, so what does this self-energy do? In the first regime of interest, big G is still small, right? So all of the action in terms of this susceptibility, at what frequencies do the mechanics respond? Well, pretty much at its natural frequency. So even though this self-energy is frequency dependent, I don't really need to worry about that. I can just evaluate this self-energy at the mechanical frequency. So we can basically just treat this as a number. Okay, and this number is going to have a real part and an imaginary part. So what are we going to do? The real part of that self-energy, I'm going to lump in with the mechanical frequency. Okay, and so that is going to be a modification of the mechanical frequency due to the optomechanical interaction. So we tend to call this the optical spring. You're getting a modified spring constant because of the light in the cavity. The imaginary part of this self-energy, I'm going to lump in with the damping, right? And that we're going to call the optical damping. Okay, so the interaction with the light in the cavity will damp the motion of the mechanical resonator. Okay, and all of this comes from this kind of simple calculation of finding the susceptibility matrix, basically inverting the dynamical matrix that's sitting in those equations there. Okay, so it's really important to understand these effects not, again, the word self-energy can give the impression that you're doing something fancy. There's a really nice, simple, intuitive way of understanding where both these effects come from. The modified spring constant, the modified damping. And again, it's really important to maybe emphasize that the understanding of these kinds of effects in the context of optomechanics really is due to sort of Vladimir Braginsky and collaborators. So Vladimir Braginsky was, as many of you probably know, an outstanding, remarkable Russian scientist who made pioneering studies, both theoretical and experimental, in this general area of optomechanics, in the areas of precision measurements. He made really, really important contributions to the LIGO interferometer as well. So he passed away last year. And this idea of understanding dynamical backaction in optomechanics, all the basic ideas, right, at the level of semiclassics, are due to him. So he has this beautiful little book on quantum measurement. It's got a very distinctive yellow cover. If this is stuff that's of at all interest to you, I really recommend checking that out. So what is the intuitive way of understanding these effects? So here's my resonance curve of my cavity. So I'm driving the cavity with laser light. Normally we think of this x-axis as the detuning of the cavity from the laser. But we know in optomechanics that when I change the position of the mechanical resonator, I also change detuning, right? So here's the normal Lorentzian response curve. If I actually now had x increase as a function of time, and now this is F, the force, the radiation pressure force on the mechanics, same thing as the number of photons in the cavity. If the mechanical position is changing as a function of time, what is the force, the number of photons, going to do as a function of time? It's going to lag behind what the equilibrium response should be, right? So I start with the mechanics at some position, the laser is really far detuned, the mechanics moves, the laser is now closer to resonance, so more photons need to enter the cavity. They can't do that instantaneously, right? This mirror is not perfectly transparent. It takes time for the photons to go in. So the idea is the number of photons in the cavity responds with a delay to the mechanical motion, right? So I can write that here. So there's the part of the photon number that is dependent on what the mechanics is doing. It depends on the mechanics. In the crudest picture, at some earlier time. You can't stop me from Taylor expanding that, right? So then that's depending on x at t plus a term that depends on the derivative of x. But now the number of photons in the cavity is the radiation pressure force. So now what do I have? I have one piece in this force that depends on x. A force that depends on x is just a spring constant. So that's the optomechanical spring, right? The real part of this self-energy. And I have a part that depends on the velocity of the mechanics, right? So velocity-dependent force is damping. That's the imaginary part of this self-energy. Okay, so that's the kind of intuitive way of thinking about this modified frequency and damping rate of the oscillator. So now let's think what happens when my mechanics is oscillating, a small amplitude, and I start with a laser detuning that's either red detuned or blue detuned. So let's start with the red detuned case, which means my laser is sitting below the cavity resonance. So now as the mechanics moves back and forth, again, as it moves forward, I'm going to follow this curve here. The cavity photon number is lagging behind, right, what the equilibrium value should be because it's taking time to build up. And then the same thing happens on the opposite leg when the mechanics is moving to the left. It takes a bit of time for the cavity to empty. So if I now think about the motion as tracing out this curve in this force versus x plane, right? Because force is the same as cavity photon number. I see that integral is going to give me something negative, right? There's a negative force, a negative amount of work being done on the mechanical resonator. This is basically cooling. Okay, so another way of saying this, and we'll see this in more detail, is I'm going to get a positive damping force from this interaction. If you do exactly the same argument, but you start with a blue detuned laser, so I'm starting somewhere on the right of this resonance curve, and now doing small oscillations, well, now the sign of that integral is opposite. I'm doing positive work on the mechanics from this interaction with the light. That's going to give me work done on the mechanics. I'm putting energy into it. That's going to give me, if you want, negative damping. This is going to give me a different kind of instability in my optomechanical dynamics. Okay, so that's the simple intuitive picture of these effects. In terms of the equations, again, this is what that optomechanical self-energy looks like. Again, this is just the world's simplest kind of self-energy coming from this linear interaction. Basically, the mechanics can sort of, if you want, hop into the cavity. Here are the cavity Green's functions. These two poles correspond to these two terms in our linearized interaction that we talked about. And again, the real and imaginary parts tell me about this spring constant effect and this damping effect. So what does this look like? So here what I'm going to plot is the induced damping of the mechanics from the light, this optical damping, this change in the spring constant from the light as a function of the detuning of the laser. And again, a negative delta means a red detuning. You're driving the cavity with the laser frequency below the cavity frequency. So if you start with the kappa of the cavity being much bigger than the mechanical frequency, you see rather broad features here. And again, positive damping for a red detuning, negative damping for a blue detuning. As you start ramping up, or reducing, sorry, the kappa of the cavity compared to the mechanical frequency, these features, this peak in the induced damping, these features in the spring constant shift become stronger and stronger. And this, of course, is just a simple fact that these poles in the photonic Green's function become sharper and sharper. Okay, so that's the, quantitatively what's happening with these effects. So as the experimentalist, you can control the size of these effects, both by how strong do you drive your laser, right? Because the self-energy scales as big G. Big G depends on the power you're putting into the cavity. But you can also control these effects by changing the detuning of the laser. Okay, so the thing I'm going to tell you more about, of course, is the cooling aspect of this and using this physics to get down to the ground state of the mechanics. Yeah. For this weak coupling regime. Sure. So to make a long story short, right? So what I said here, let's just focus on the self-energy at the mechanical frequency, right? So when is that really a valid thing to do? Well, what I'm saying is, okay, look, this mechanical Green's function, this whole susceptibility, it has well-defined poles. It's something like the mechanical frequency, and those poles are broadened, right? Those poles are broadened initially just by the intrinsic mechanical damping. Eventually, they're also broadened by this optical damping. So now what is the self-consistency condition for ignoring this frequency dependence? Well, there's some characteristic scale over which this sigma changes with frequency. How does that compare against the width of your pole? So when this tends to break down, right, the upshot is when this big G is actually on par with kappa. Okay? And then what happens, it's not that surprising, you have two coupled harmonic oscillators, you get normal modes. Okay, so that's the regime. I'm not talking about that right now. I'm talking about a weak enough regime where my mechanics is mechanics, my photons are photons, but the mechanics are slightly modified. Yeah. Okay, so the thing I'm not going to spend too much time talking about here, but it is kind of fascinating, and who knows, if there's time, maybe we'll get to it. What if you do detune your laser to the blue, and you do get this negative damping, right? And so, yep. Okay, yeah, so good question. So this is what I called delta prime before. So, okay, if you wanted to actually use the real laser detuning, there'd be a little bit of a distortion to this curve, right? Because the cavity frequency is also changing depending on how many average number of photons I put in, right? So I'm basically kind of including that in this delta here. For the weak kind of couplings that we're talking about here initially, that's not going to be a huge effect. Okay, yeah. So this is the detuning, including the mean field shift of the cavity frequency. So if you drive on the blue, you get negative damping from this optomechanical interaction. If I crank up the laser power, that negative damping can overwhelm the positive intrinsic damping of the mechanical mode. Right? So then what happens, now depending on who you are, you can use all sorts of words. You could say that we're going to get limit cycle physics, we're going to have an oscillator. If you want to be much more dramatic, you could write a paper and say, we have a phonon laser, right? So I'm not going to comment on what the right thing to call it is. What is actually going to happen? Your mechanical motion is going to start to grow exponentially in time, right? That's what negative damping is, an exponential growth of amplitude with time. So what does that mean? Well, at some point, the mechanical amplitude starts to get really, really large. All of this linearization stuff doesn't work anymore, right? So even if you start with an intrinsically weak coupling, if the mechanics is moving enough, it's going to have a dramatic effect on what's going on in the cavity. Okay, so this actually turns out to be an interesting thing, right? Because this says even for a weak coupling system, you can get pushed into sort of strong coupling. Because now the idea is at some point, the amplitude of these oscillations is going to saturate. And in the ideal case, where is that coming from? It's coming from the intrinsic nonlinearity of the system. It's coming from the fact that the large amplitude of oscillations in the mechanics is changing the way the cavity is providing this negative damping, and it's causing that negative damping to drop off in magnitude. Right? So the standard way of thinking about this is effectively this optical damping is actually, it's nonlinear damping. It's a function of the amplitude or the energy of the mechanical oscillations. Okay, so what does this normally lead to? So classically, you would end up having this kind of self-oscillation state, where roughly speaking, the amplitude of oscillations is fixed. The phase is not fixed at all. This is not like having an external drive on the oscillator, right? So the phase would slowly diffuse in time, just like in a laser, right? So if we think about this quantum mechanically, and again, it'd be fun to get to this if there's time. We think about this quantum mechanically, and I thought about a Wigner function describing what the mechanics is doing. This limit cycle where the amplitude is well defined, but the phase is diffusing, if I time average that, in phase space, that would just look like a ring, right? So it would be positive everywhere. It'd be a kind of classical state. The amplitude is not perfectly well defined. The ring has some width. But again, and the phase is completely ill-defined. It's just circular. So the interesting thing in optomechanics is now, what if you really worry about the nonlinearity at the quantum level? Well, then you can get into a regime where this classical self-oscillation physics actually gives you a mechanical self-oscillating state that is not classical. So that is, it's described by a Wigner function that has negative bits. Okay, and the interesting thing about this, right, so the thing I kept emphasizing, right, so we have our fundamental optomechanical interaction. And the problem is this G is much, much smaller than the damping rates relevant in the system. In particular, it's much, much smaller than the damping rate of the cavity. So normally we think that, okay, that little g doesn't play any role. We're not going to see interesting quantum effects if little g is much smaller than kappa. This physics can actually occur even if little g is much smaller than kappa. Okay, so this is kind of, we'll have more to say about that, I'll have more to say about that a little bit later. This kind of non-classical limit cycle physics, in principle, I'm not saying it's easy, but even if you have a very, very weak single photon, single phonon optomechanical coupling, you could still get this kind of interesting self-oscillating state. Okay, so hopefully more about that later. Or again, if I don't get to it, feel free to ask me. Let's turn to the other side of things, right? The other side of things is this cooling physics out here where I get extra damping. So at first glance, extra damping sounds terrible, right? Why would I want to reduce the Q factor of my oscillator? So what I want to convince you now is extra damping is actually cooling in this context. This is a way of getting to the ground state. Okay, so let's just think about things classically for a second. Classically, how would I describe a damped harmonic oscillator? I'd write down a classical Langevin equation. So here is my damping. Maybe it's not even local in time. Associated with that damping is a corresponding thermal Langevin force, right? And this thermal Langevin force has to have exactly the right properties to keep me in thermal equilibrium. So the size of that thermal Langevin force, its spectral density, is proportional to the damping at that frequency and proportional to temperature. Okay? So now what's the crude idea with this optical damping giving me cooling? If I had a way of adding damping to this equation, but not adding any force fluctuations, right? Well, then I'm basically going to get a lower effective temperature, okay? And so the question is, in the semi-classical theory, right, we didn't include any fluctuations at all, so we could capture this damping effect. But if there is extra noise driving the mechanics because of the interaction with the light in the cavity, the semi-classical theory doesn't tell me that. So the question we have to ask is it really just this simple, right? Is the interaction with the cavity just adding some damping, or is it also adding some extra thermal noise? And you might say, well, look, this is trivial. You have fluctuation dissipation. If you know the damping, you know what the force is. It's not that trivial because your driven cavity is not a thermal equilibrium system, right? So to figure out what the force fluctuations are, we actually have to calculate something. Okay, and what I'm going to do, now one way, the simplest way of doing it would just be to use these equations and actually keep track. In the quantum case, we have the noise terms here. So in a few lines, you could derive all of this using those quantum Langevin equations. I'm going to do things in a much more, well, not much more, but a slightly more complicated way that's more general. Okay, and the virtue of that is it'll give us a language and a way of thinking about this idea of using a non-equilibrium system as a bath to cool your system of interest in a more general way. And that's going to let us describe other kinds of cooling that turn out to also be very, very useful. Okay, so again, classically, I have this kind of Langevin description. To understand the temperature of my oscillator, I need to know both its damping. I need to know the statistical properties of these random forces that are driving it. Okay, so the way we're going to do, and again, something that we should also emphasize is what do I mean by this spectral density? So again, these are introductory lectures. This spectral density, so if I have some random force as a function of time, again, all of this is classical, I could always Fourier transform that. And the Fourier coefficients of this stuff, those are also random variables. Okay, so on average, that Fourier coefficient on average is 0. But on average, its modulus squared will be non-zero. So this spectral density that we're talking about is really asking what's the variance of the size of the force fluctuation at a given frequency. Okay, and in one or two lines of algebra, this quantity here, what is the average, the ensemble average of that fluctuating force at a given frequency? You can relate that to the Fourier transform of the autocorrelation function of the noise. Okay, this is the Wiener-Khinchin theorem. Okay, so again, the idea is in our system, I want to understand these fluctuating forces coming from the photons in the cavity. So this force that I'm interested in is going to be the photon number in the cavity. We want to understand, in a sense, what is the temperature associated with this bath that's presented by the cavity. Because that's the ultimate temperature that I'd be able to cool my mechanical resonator down to. So the idea is, let's also try to think about the force coming from my non-equilibrium system, this driven cavity, the way we would think about things classically. Right? Is there a question? Yeah? No, so here, now I'm going to tell you about is kind of very, very general way. And what's nice about this is, so for the next little bit, you can ignore that set of Langevin equations. This is going to be something that's valid anytime I couple my system of interest, here the mechanical oscillator, to some non-equilibrium system that's going to act as a bath, and that coupling is weak. And the idea is, by understanding the noise properties, the quantum noise properties of this non-equilibrium system, I'm going to be able to understand what it does to my system of interest. And this is really, really general, and it's going to involve just being able to calculate the noise properties of the non-equilibrium system. How you choose to do that is up to you. Right? The way the theory works is completely general. Yeah, so that was kind of like trying to whet your appetite for something I might get to later, right? So that comes from treating the full nonlinearity of the problem, no linearization. The plots that I showed you there were actually from a master equation simulation. So working with, again, Clemens Hammerer and Florian Marquardt, there's even a kind of analytic theory that lets you say things about those non-classical Wigner functions. But that is going beyond everything I'm saying here. That's a treatment where you have to deal with the full nonlinearity. Yeah. Okay, so how do I generalize this idea of a force noise spectral density to quantum mechanics? What's the usual thing, right? You have something classically that makes sense. You want to make it quantum mechanical. You add hats on things, and then you hope nothing bad happens, right? So I can take this definition of a force noise spectral density. I can now make it quantum mechanical by putting hats on my Fs. So my force operator is now, it's an operator. So in our case, it's proportional to the photon number in the cavity. And now the first thing you have to worry about is, well, unlike the classical case, and again, this average here, this is an average of two Heisenberg picture operators for the cavity with no optomechanical coupling. So this is going to be a theory that describes the effects of the cavity on the mechanics and the weak coupling limit. It's kind of a perturbative approach. The idea is we need to understand the properties of the driven cavity, the non-equilibrium system on its own first. Okay, so that's what that average means, just over the uncoupled cavity, Heisenberg picture operators. The problem is, unlike classical forces, f of t and f of 0 don't commute, right, at different times. And what that means, and you can convince yourself of this in one line, unlike a classical noise spectral density, this thing is not the same at positive and negative frequencies. Okay, so that's the first thing we have to grapple with. So how do we think about that? Well, again, quantum mechanically, I could always write this correlation function in terms of whatever the unknown energy eigenstates are of my reservoir, in my case, this driven damped cavity, and in terms of its density matrix. Okay, I'm assuming that I have a kind of stationary state for this non-equilibrium system. So this is what people call a Lyman representation. So another way of writing exactly this same quantity is this sum over what look like golden rule transition rates, right? So if I look at the spectral density at a given frequency, this quantum spectral density, I'm basically summing over all transitions where the operator f can take me from state I to little f, where the change of energy is either uphill in energy or downhill in energy. And so in particular, omega greater than 0 corresponds to a transition where the bath goes uphill in energy, so little f has more energy than little I. So the bath is absorbing energy. Omega less than 0 corresponds to the opposite thing. The bath is emitting energy. So this asymmetry between positive and negative frequencies really tells me about the asymmetry between being able to absorb energy and being able to emit energy. So what if the bath was in thermal equilibrium? The bath is in thermal equilibrium. I know something about its density matrix. And not surprisingly, what you can show is if the bath was in thermal equilibrium, you know what that ratio is, okay? What's the relative, probability for emission versus absorption at a given frequency? It's just given by a Boltzmann factor. Okay, so the idea is there's a connection between the asymmetry of this noise spectral density between positive and negative frequencies and the temperature of my bath if my bath was in thermal equilibrium. So in our case, the bath is this driven cavity. It's not in thermal equilibrium. So what can I basically do? I can use this ratio to define temperature. Okay, so this is basically like using the fluctuation-dissipation relation in reverse. You tell me some damping, you tell me some noise properties, I take the ratio, I will define a temperature from that. So here, the equivalent thing is, if I know this noise spectral density at negative omega and positive omega, the ratio of those will define this effective temperature. What's the price I pay for being out of equilibrium? If I now look at the same quantity at a different frequency, I'm going to get a different effective temperature. Okay? Mm-hmm. So in equilibrium, so this is a very, very general statement. In equilibrium, right, this is going to be a thermal density matrix, right? And the I's here are labeling energy eigenstates. So now when I calculate that ratio, the ratio from going from I to F and F to I, it's going to boil down to the ratio of the occupancies of the initial and final states. That's where I'm going to get my thermal factor from. So it's all coming from the density matrix. Okay, and so in our case, we're using this as a definition of effective temperature. You can't stop me from defining things like this. You could wonder, what possible relevance does this have, right? And to give the full answer of that, and you can even skip this here, I'm going to hint at a calculation that you can do, and there's some references here. To some of you, maybe this will make sense. So in this weak coupling regime, I'm very, very weakly coupled to my bath. The only things about my bath that are going to matter are its Gaussian noise properties. I'm not going to need to worry about the fact that maybe I need to look at a correlation function of 4 F operators. And maybe that doesn't factor the way I would get from Wick's theorem. For weak coupling, that kind of stuff doesn't matter. So for weak coupling, any bath looks like a Gaussian bath. Any bath looks like a bath of harmonic oscillators. And if I really just coupled my system to a bath of harmonic oscillators where F was linear in the coordinates of the oscillators, you could always rigorously integrate out that bath, even in the quantum case, and derive a very classical-looking Langevin equation. So in this classical-looking Langevin equation, the damping is basically set by the asymmetry in that force noise spectral density. So the difference between, I'll get the question in 1 second, between absorbing and emitting, right, which kind of makes sense. The damping is the net effect of those kinds of transitions. And this classical force noise spectral density, the thing describing this guy here, is just the symmetric part of this quantum spectral noise density. Okay, so this is something that for weak coupling, my non-equilibrium bath, right, I can really treat as a bath of harmonic oscillators, okay, with exactly the same, if you want, 2-point correlation functions. I can really derive this classical Langevin equation. And now classically, you could imagine saying, well, look, classically, it does seem not completely unreasonable to define temperature at a given frequency using the fluctuation dissipation theorem. And that's exactly what I'm doing, right? That's completely equivalent to this definition here. Okay, so again, this non-equilibrium system basically gets described by a frequency-dependent effective temperature. Okay, to figure out what that frequency-dependent temperature is, I need to calculate the quantum noise properties, right? This correlation function of whatever this force operator is. Okay? And if I think about physically a non-equilibrium system, what do I mean by an effective temperature? This is something that has the units of energy, if I put a KB there. That is basically an energy scale characterizing the asymmetry between absorption and emission. Right? So that's a notion I can have without any statement about being in actual thermal equilibrium. Again, the price we pay for not being in thermal equilibrium is this guy depends on frequency. The good news is, for the problem of interest, we know what frequency we need to look at. our mechanical resonator is a high Q object. It's going to be relatively high Q even when I have this optical damping. I only need to evaluate all these quantities at the mechanical resonance frequency. That's the only frequency at which the mechanic sees this damping, sees this random force. So at the end of the day, what we want to understand is, what is this effective temperature at the mechanical frequency? So Nicolas, I think I put off a question you had, sorry. So in the present system, so again, the answer to that question is sort of system specific, right? So what are you throwing away? Well, you know, that's a unique answer for every different system you could think about. So here, the weak coupling assumption, right? So our force noise is going to be the photon number fluctuations in the cavity, and maybe that's even on the next slide. So this is what the situation is for our system. Our system is this driven cavity, right? We work in this displacement picture. Our force is basically the fluctuating part of the cavity photon number, okay? And so the kind of approximation that I'm making, I'm throwing away the non-Gaussian part of the intrinsic fluctuations of the cavity photon number. If I really think about the cavity photon number, there's this part that's linear in D. So this is really like the amplitude quadrature of fluctuations. There's also a D dagger D here that I'm throwing away. Okay, so the validity of this, at least the naive validity of this, is you need to have a large number of photons in the cavity. Okay, because I'm ignoring the non-Gaussian aspects of the cavity photon number fluctuations. And so that approximation is controlled by why is this bigger than the D dagger D that's missing here. It turns out in this system, it's even a better approximation than that, and I can tell you more about that later. Okay, so in this system, this is my force, right? The cavity photon number fluctuations. Here I've linearized A dagger A becomes basically this A bar times D plus D dagger. To calculate this force noise correlation function, I first have to look at this time-dependent correlation function. And again, that just boils down to if I'm assuming that my cavity is driven by vacuum noise, that just boils down to the correlation function of D of T, D dagger at 0. That's trivial to calculate from these Langevin equations, because what's the dynamics of D? Again, we're doing this for no optomechanical coupling, right? For no optomechanical coupling, I just have a damped oscillator. So this correlation function, the prefactor of alpha, the average number of photons coming from the coherent drive, that gives me this n-bar cavity prefactor. And then what's left here is just the damped oscillations of my cavity lowering operator. So it oscillates now, we're in this rotating frame at the detuning of the laser frequency from the cavity frequency, and I have this damping from just the kappa of the cavity. Okay, so that's what things look like in the time domain. What I need to do is Fourier transform that. This is just going to give me a Lorentzian that's shifted from 0. Okay, so now it's kind of easy to see in this picture how cooling works. Sure, go ahead. Sorry, so no, so this thing here, right? So this gamma here, if I had written this correctly, this is a causal function, right? So if you want, this is the same thing as what you would get by looking at the retarded Green's function of this force noise. So there's an explicitly causal function that describes the force terms that are showing up here, the non-fluctuating force terms. The real part of that I've lumped into a change in the spring constant. The imaginary part of that retarded force Green's function, that's what gives me damping. Okay, and the retarded part, or the imaginary part of that Green's function, I can always relate to this asymmetry in the spectral density. So this is explicitly causal, yeah. This one here, or this, or this? Yeah. Why? So there's no notion of time here. So this is just a noise spectral density. Yeah, so I don't think there's any, so this is just at every frequency, so just think of this as a classical random variable, right? So delta F at T is a classical random variable. I could Fourier transform that. Delta f of omega is a classical random variable. I'm just asking about how big is the variance of each one of those classical random variables. And this is just the size of the fluctuations at a given frequency. So I don't think there's anything that useful to try to connect that to sort of time reversal. So this, what I've written here, so this is what would be the classical fluctuation dissipation theorem if this was really temperature and it was much bigger than h bar omega. This is just the quantum fluctuation dissipation theorem, but now with this effective temperature as opposed to the temperature. So what I am assuming about the non-equilibrium system that's my bath is I'm assuming it's in a steady state. It's in a time-independent state, which means that its correlation functions depend on one time and not two. Okay, so if and that's an interesting wrinkle that you can then start to think about, if my non-equilibrium system, my driven cavity, right? Imagine I have a more complicated driving situation where its state is explicitly time-dependent. Then, these correlation functions that the f of t prime correlation function, it depends on both times. It doesn't just depend on the time difference. Then you have to modify how you think about this theory. Because then all these spectral densities depend on two frequencies, not one. Okay, that's not the case here, not the case in a lot of cases, but that is something that you can kind of, expand this theory to try to take into account. But we don't have to worry about that. Yeah, so here, my real question here is how is this non-equilibrium system driving my harmonic oscillator? So now you can ask, okay, this step of deriving this equation and saying it's rigorous, if I had nonlinear terms in the harmonic oscillator, well then that derivation also, becomes approximate. So then, if you wanted to use this same approach to understand how are you cooling a highly nonlinear harmonic oscillator, then there are additional corrections that would show up from the fact that this effective temperature is not enormous compared to h bar omega. Okay, and this is already a problem if you just think about coupling a nonlinear oscillator to a harmonic bath in equilibrium, and you try to rigorously derive this kind of classical quantum Langevin equation, right? That then becomes an approximation. It's only exact when your system of interest is harmonic, right? For other cases, it's effectively a high temperature approximation. Well, so in the high temperature limit, all of this would still be valid. And then the fact that you have kind of additional quantum corrections, that's not unique to the fact that you've coupled to a non-equilibrium system, right? That's really the nonlinear of the oscillator just matters, right? Even if you couple to an equilibrium bath, yeah. The flux, yes, absolutely, and we'll. Sure. Well, basically, it's basically that theory, right? So the harmonic oscillator in the cases that we're interested in are linear, right? So when I talked about deriving that susceptibility, right, that mechanical Green's function that had that self-energy, that told me how the mechanics responded to some external force. It also tells me how it responds to some fluctuating force, right? Harmonic oscillator is linear. It responds linearly to whatever force you apply to it, whether it's stochastic or not. So that will tell you the shape of the mechanical spectrum you expect to see. And this is measured all the time in optomechanics. Manas, did you have a question? Or? So I completely and strongly disagree in every possible way. So look, and this was actually a problem in this whole area for a long time. So there were people that for every, so before cavity optomechanics kind of swallowed quantum electromechanics, people were kind of coupling a mechanical resonator to you name the system, right? So a quantum dot, a double quantum dot, more complicated quantum circuits. In every case, someone would do a specific calculation for that specific system, and through some miracle of theory say, hey, wow, it's amazing. The mechanics ends up in a thermal state at some effective temperature set by the voltage, set by some scale. And someone would do it for another system and say, hey, look, I found the same thing. This is amazing. I've coupled to a non-equilibrium system, and I have an effective temperature set by some parameters. And so it's not amazing, right? There's a general structure that lets you understand that, no matter what the non-equilibrium system is. It tells you what the price you pay is for being out of equilibrium, right? And it gives you a generic way of thinking of what this scale is, right? So no matter what the non-equilibrium system is, what is this effective temperature? It's the energy scale that distinguishes absorption from emission, okay? So I think it is a very useful notion. And I'm going to give you examples. I'm going to give you 3 different cases where you can use this approach to understand what's going on. Absolutely. So you could map this onto, so the regime I'm talking about where effectively I'm only worrying about the bath at the Gaussian level, you can map everything onto having an effective oscillator bath, right? So I have some spectral density of oscillators that will determine this damping kernel. But now the oscillators at different frequencies are at different temperatures, right? So that's a well-defined, if you want, generalization of a kind of Caldera-Leggett model, right? And what that effective temperature as a function of frequency should be, we can calculate that from specific models. Okay, so this is definitely a useful, maybe Michelle wants to. Well, so I think the point here is I'm using the fluctuation dissipation theorem in reverse. I don't have it, but I'm defining a temperature from that. And yeah, anytime someone just defines something, I think it's valid to ask, well, you can't stop me from defining that, but is it of any utility? Right? So for example, in this specific problem, this effective temperature I'm going to get, right, that's a function of frequency, that is going to tell me how cold can you actually cool your mechanical resonator. And how does it depend on the frequency of the mechanical mode. And again, the same theory would work. You decide to couple your mechanical resonator to some horrid superconducting single electron transistor or whatever, the same approach is going to work. It's just, look, it's a different bath, it's a different force operator. It's still the same effective temperature, right? So for me, at least, this has been a very useful way of taking a lot of very disparate results and having a common way of thinking about it. Well, but I think it's, this approach still works, right? So this approach, everything I've written here works, even if the T effective is strongly omega dependent. When does it just look like a simple bath where you just see one temperature and not this frequency dependence? Well, then you have to have a narrow enough line width of your system where you only look at this at a single frequency. But imagine, for whatever reason, you have a terrible Q oscillator and you can actually see that frequency dependence. Your oscillator will end up in a non-equilibrium state. This theory will describe what happens, right? So it's still a useful notion. So I am not assuming anything about the density matrix, let me finish, about the density matrix of the system that's acting as the bath, except that it's in a stationary state. And I'm assuming my system of interest couples weakly to it. Those are the only assumptions that are going into this. What driving? So the general theory here, I haven't specified any kind of driving here, right? The general theory I've told you up to this point, I haven't told you anything about the system producing this F. I'm just saying there are some correlation functions you can calculate, right? So I do need the system, if it's a driven system that's producing this force, I do need it to relax into a steady state that's time independent. That I am assuming, right? If I didn't want to assume that, there are ways of generalizing it. It gets more complicated. But besides that, you know, all of this is derived. That's the beauty of it. It's derived without having to tell you a lot of details about the system that's involved. Once I have this machinery, I know what the system is now that I'm interested in. I calculate these objects. I figure out how cold I can be.
Sorry.
Yeah, okay, so that's getting a little bit further on, but you know, hold on to that question. So what I want to do now is basically take this approach, which might seem so abstract as to be completely useless, and apply it to the cavity cooling problem. And again, rederive a result that you could probably have guessed, right? And then show you how it works in a context where I don't think you'd be able to guess what the answer is, okay? To show you that it actually has value. So then if you want to ask your questions about, you know, that, ask me again towards the end. Okay. And again, maybe something else I can comment, right? You know, I don't want to use fancy terms without any reason to. All of the things I'm describing here too, right? You can phrase all of this in the language of sort of Keldysh-Green's functions, right? So this idea of thinking about an effective temperature for a non-equilibrium system, this is essentially the same thing you would do within a Keldysh framework. Okay, I find it useful to describe it like this because from past experience, the word Keldysh, especially to experimentalists, can be a bit of a turnoff, right? But if that's your thing, right, this is really an equivalent way of describing things. Okay, so let's apply this to the cavity cooling problem. Yep. So again, I completely disagree, and let me give you a statement, okay? Imagine you have a mechanical oscillator, and you're able to tune its frequency. Okay, and imagine we've coupled to this bath, right? This driven cavity. So you start with one frequency. The cavity is the bath that determines the state of the mechanics. The mechanics is a very narrow line width. You end up at the effective temperature for the mechanics at its frequency, omega 1. Now you change the frequency of the cavity, change the frequency of the mechanics to something very different. Still coupled to exactly the same cavity, driven the same way. You find that the mechanics is now at a different temperature. What's that temperature? It's T effective of the new mechanical frequency. So there's an operational meaning to that quantity. Even though this temperature depends on frequency, you could probe it just by changing the frequency of the mechanical resonator. I think maybe this will make more sense if I actually discuss this in the context of a real, the real systems, as opposed to we can argue about abstract things forever. If we put it in the context of something real, it might seem a little less threatening. Okay, so also great, discussion topic for coffee, tea, cookies, all that. So if I apply this theory to this driven cavity, right, what is this quantum noise spectral density? It's just a shifted Lorentzian, right? It's the Lorentzian density of states of the cavity with the width kappa. There's a prefactor that's the number of coherent photons in the system, and it's basically centered at a frequency that's negative of the detuning. So if I pick a red detuning, which means delta is negative, this Lorentzian is centered on a positive frequency. Okay, and in particular, imagine I pick the detuning to be minus omega mechanical. So I drive with the red detuning equal to the mechanical frequency. So then the peak of the Lorentzian is sitting right at SFF of plus omega m. Okay, so the positive frequency noise, which is telling me about absorption, sees this peak in the noise. The negative the noise spectral density at negative the mechanical frequency is detuned from the peak of that Lorentzian. So this is a case where positive SFF is much bigger than negative SFF. Absorption is much, much stronger than emission. I'm going to get a very, very low effective temperature. Okay, and so from this theory, I just take the ratio of this guy at positive frequency and negative frequency. I equate that to a Boltzmann factor. That is going to be the temperature that my mechanical resonator relaxes to. Okay, so again, this is actually talking about the kind of experiment I was just describing. So imagine now you have the same cavity, and you either couple to it with a very, very low frequency mechanical resonator, omega m much smaller than kappa, or a very, very high frequency mechanical resonator, much bigger than kappa. So in the low frequency limit, right? So in the low frequency limit, I don't know, plus omega m is sitting there, minus omega m is there. There's not a whole lot of asymmetry between the positive frequency noise of interest and the negative frequency noise of interest. A lack of asymmetry when absorption and emission are almost the same, that corresponds to a high effect. So when you go through express the effective temperature, not as a Boltzmann factor, but as an effective Bose-Einstein occupancy factor, so a thermal number of quanta, what do you find? You find that the effective temperature of the cavity, which is the temperature that the mechanics will relax to in the ideal case, is much, much bigger than 1 in units of quanta. It's given by the ratio of kappa over omega m with this factor of 4. Okay, so in that regime where the mechanical frequency is small, this same cavity, right, it's always the same cavity, has a very, very high effective temperature, right? It has a very high thermal occupancy as seen by the mechanics. If I now do the same thing, but use a very, very high frequency cavity, a high frequency mechanical resonator, and again, I pick this detuning such that the peak of this noise spectral density lines up with the mechanical frequency, well, in that case, the positive frequency noise is enormous. The negative frequency noise, that makes this Lorentzian even skinnier and skinnier and skinnier, is basically zero. So in that case, I have lots of absorption. I have no emission. That's effectively a zero temperature bath. So in that case, the effective temperature seen by the mechanics coupling to exactly the same cavity is much, much, much smaller than 1 in units of kappa. Okay, so in that case, and this is kind of the limits of cavity cooling in this sideband resolved regime, this effective temperature is going to 0 as the ratio of kappa, the cavity line width, divided by the mechanical frequency squared. Okay, so again, it's the same cavity in both cases. What temperature does the mechanic see? What thermal occupancy can it reach in the two cases? It depends on its frequency. Okay, in one case, it looks pretty hot. In the other case, it looks really cold. Okay, so again, this is my exhibit A in defense of the notion of a frequency-dependent effective temperature. So that's even going back to sort of deriving these kind of Langevin equations. So there, the important thing was, I have to think about deriving the Langevin equation for the cavity. That's one thing. I have to derive the Langevin equation for the mechanics coupled to its bath as well. So there, what I'm assuming is the mechanical frequency that sets the frequency at which I'm looking at the noise coming from the intrinsic sources of mechanical dissipation. I'm assuming that its line width is narrow enough that the density of states of the intrinsic mechanical dissipation looks pretty flat. So there it's a difference. So that's really something about the quality factor of the mechanical resonator. So that doesn't involve the kappa of the cavity. Okay, so the thing I talked about in the last lecture was not about the mechanics talking to the cavity. It was trying to derive the term on the right-hand side of each of those equations. Cavity talking to its bath, where I compare kappa compared to the cavity frequency, and the mechanics talking to its own intrinsic bath, right, to its own internal sources of dissipation. Not for that. Yeah, so with this kind of linearized coupling as well, the fact that the mechanical frequency could be large, and thinking about this photonic dissipation, you would still like the mechanical frequency, right, to be much smaller than the cavity frequency, right? So even though the mechanical frequency is 10 times kappa, it's still enormously small compared to the cavity frequency. So it's still safe to say that we're still pretty much looking at the photon modes outside of the cavity, near the cavity frequency, right? We're talking about hundreds of terahertz. If I shift by 10 megahertz, it's still okay. Yeah. Okay, so we have this cooling physics. So again, to really understand the cooling physics, of course, we have to also worry about the fact that the mechanical resonator is not just coupled to the radiation pressure force. It's not just the cavity photons that act like a bath. It also has its own intrinsic sources of dissipation, which left to their own devices would put the mechanical resonator in thermal equilibrium. So what do you actually find? At the end of the day, what is the thermal occupancy of the mechanical resonator in as a number of quanta? It's basically a weighted average of what is the effective temperature of the cavity. So here I've called that N bar BA for the backaction temperature if you want. It's this quantity here, that small quantity. And then the first term here is the weighted contribution of just these intrinsic thermal fluctuations of the mechanics. Okay, and how do I do the weighted average? Well, I basically think of how strongly am I coupled to these two sources of dissipation. And what's the strength of the coupling? Well, how big is the optical damping, the damping coming from the interaction with the photons in the cavity? And how big is the intrinsic damping of the mechanics. What would its damping rate be if I had no coupling to the cavity? Right, so at the end of the day, I could just take this expression, divide everything through by this intrinsic gamma naught, right? And so the thing that controls, can I kill this term and only effectively be coupled to the cavity dissipation? It's the ratio of this optical damping, this, radiation-induced damping, to the intrinsic damping. And so what does that turn out to be? Well, if I take this good cavity limit, the good cavity limit is where the mechanical frequency is much bigger than kappa. If I pick this ideal laser detuning, detuned to the red by omega m, that optical damping is just 4 big G squared, the many photon optomechanical coupling squared, divided by kappa. So at the end of the day, the parameter that's controlling this cooling, the ratio of these two damping rates, the thing I want to be large, it's just this parameter I hinted at last lecture. It's this optomechanical cooperativity. Okay, so in cooling, that's the parameter that really controls. Can you really just effectively be thermalized with the cavity? Okay, and it turns out in this linearized regime of optomechanics, this is pretty much the parameter that controls everything that you might see. Okay, so I have like 4 minutes or so. And so I think I showed you, last class or last lecture that there are lots of experiments now that have implemented these ideas. This is showing, as you vary the good cavity parameter, how big is the mechanical frequency compared to kappa. The blue curve is showing you what is this ultimate limit in terms of how cold you can get. This is basically showing you what is the effective temperature of the cavity, okay, as a number of thermal quanta. These are various experiments that have exploited this physics. And I told you about this experiment from Cindy Riegel's group, where they're actually able to hit this kind of fundamental limit. Okay, so in that experiment with a vibrating membrane, a silicon nitride membrane of maybe 1.5 megahertz, they're actually able to get down to a thermal occupancy of 0.2 quanta. Okay, so that's, that's an effective temperature of microkelvin. So of course, there's an issue with this cavity cooling, right? Which is ideally, if you want to do macroscopic quantum mechanics, maybe you were motivated by that, testing if there's gravitational effects that give you decoherence, you'd like to work with something really, really massive. Really, really massive typically means really low frequencies, right? So what if you're out here and you still want to cool to the ground state? So as beautiful as this cavity cooling physics is, doesn't seem like it's going to really help you reach the ground state. And the other thing you might worry about, and do I have a slide that shows this nicely, you might also think that, okay, all this effective temperature business, this quantum noise stuff, this is huge overkill for this problem. All I'm describing at the end of the day is Raman scattering, right? And if I detune correctly, right, like shown here, if my laser light comes in and absorbs a phonon, it sees the large density of states of the cavity, there's a big probability, a big rate for that process. If my laser light comes in and tries to Stokes scatter and actually emit a phonon, there's no density of states. So all this quantum noise business seems like overkill. This is just density of states physics, right? Why am I calling it this? So let me give you an example in 2 minutes, right, of using this quantum noise formalism in a modified optomechanical system where you can cool to the ground state even if the mechanical frequency is much smaller than kappa, and where this quantum noise physics is no longer a really tortuous way of describing a density of states. Okay, so this is work that I did with a postdoc, Florian Elsta and Steve Gervin, I guess a number of years ago. So the basic optomechanical system, what do we have? We have a cavity frequency that depends on x. So I'm a theorist. You can't stop me from thinking about a system where maybe kappa, the transparency of that mirror, also depends on x. That's another kind of parametric coupling I could have. And it's not totally crazy to think about. So imagine a circuit implementation where my cavity is an LC oscillator, my waveguide is now a transmission line, and the coupling to that waveguide to the cavity, the LC oscillator, there's some coupling capacitor, and that coupling capacitor, it can vibrate, it's x dependent. So effectively in that case, the kappa of this cavity, its damping rate, will depend on the mechanical frequency. Okay, so skipping lots of details,
here is this quantum noise spectral density, this SFF of omega, positive frequencies cooling, negative frequencies emission. This is what you have if you just have a standard optomechanical coupling, this Lorentzian density of states. I've actually picked a blue detuning. So this is bad for cooling because look, the peak is actually at negative frequencies. And now when I actually add this funny kind of coupling, this kappa of x, this is now what this quantum noise spectral density looks like. Okay, so that is not a Lorentzian density of states, right? If you stare at that longer, you'll realize that's a Fano resonance. And the idea is there's a kind of interference that determines this quantum noise spectral density. You can tune that interference to have exactly a zero at SFF of minus omega m, right? So at negative frequencies at the mechanical frequency, that's what controls emission. If I can make that zero, I'm coupled to a bath that can never give me energy. That's exactly a zero temperature bath. Okay, so in one slide, why would you get such a wacky Lorentzian or Fano line shape? Fano line shapes come from interference, from a kind of direct process and a resonant process. In this system, there's two ways for the quantum noise to basically reach the mechanical resonator. And I am pretty much done. So the noise can come in through this transmission line, directly reach the mechanics, or the noise could first go into the LC resonator, spend some time there, and then come back out and hit the mechanical resonator. So this is the kind of direct process you need for a Fano resonance. This is the resonant process. You can tune the interference of those two things by playing with the detuning of your laser. You can get this perfect zero temperature result, this interference. There's no condition on needing the mechanical frequency to be small. This now has nothing to do with density of states physics. So it's not about just having a very narrow density of states. This is about interference. Getting that interference to work is not reliant on this good cavity condition. And just the last thing I'll sketch is this has actually been recently implemented in an experiment, again, motivated by gravitational wave style detectors. So this is a Michelson-Sagnac interferometer. This is in the group of Roman Schnabel in Hanover. And the crude idea, and I'm out of time, this complicated collection of mirrors with a moving membrane in this one arm, that's effectively like having one compound mirror at the end of this effective Fabry-Perot, whose kappa, whose transparency, depends on the mechanical position. Okay, so in this experiment, they were really able to show not cooling all the way to the ground state, but a dramatic amount of cooling of a very low frequency mechanical mode, 100 kilohertz, where your kappa is, an order of magnitude bigger. Okay, and so moving forward and even thinking about these LIGO-style detectors, where again, you have really, really massive suspended mirrors, having cooling strategies like this could be a real boon. And it's also hopefully exhibit B for why this quantum noise approach, this idea of thinking about an effective temperature, is indeed a useful way to look at things. Okay, so this thing is flashing red, it's making me nervous. I'm gonna stop there and thank you for your time.
Thank you very much, Aashish, for the very interesting lecture too. We have, we have many questions. Okay, let's start slowly from the first line.
They did, yeah. I want to say it's close to like a factor of 10. It's been a while since I looked at it in detail, but they did do better than what they could do if they did the conventional technique. There's something else that's nice about this physics. So for gravitational wave type applications, it's not just this cold damping that's useful. It's actually useful to make the mechanical resonator a lot stiffer, to push its frequency up. And so normally to do that, you have to have a blue detuned laser. And that's bad because that gives you self-oscillation. So with this physics, you can get this optical spring, make your mechanics higher frequency without having any instability. You can do it with a red detuned laser. So that's something else that they kind of explore in this work. Yeah, exactly. So, okay, so it's a bit more complicated, right? So The whole point of this quantum noise picture is, yeah, I care about the noise at the mechanical frequency, but I got to worry about plus omega m and minus omega m. So the idea is that this interference only occurs at negative frequencies, not at positive frequencies. So the noise that's responsible for emission of energy to the mechanics has this perfect destructive interference. The noise that's responsible for absorption, it better not also have that, you know. If that also was zero, well, then nothing happens, right? So the interference is only happening for the noise at minus omega m, the noise responsible for exciting the mechanics. Again, there wasn't a huge amount of time, so I don't feel like bad for sweeping some nasty things under the rug. The nasty thing under the rug is, for this to work in the way I've described, in this kind of electromechanical setup where it's a cavity, you need to be highly overcoupled, right? So I need this interference that the noise can hit the mechanics two ways and interfere. If there's some other nasty port of noise coupled to this cavity that's also sending noise up to the mechanics, that's not going to get canceled anymore, right? So you need to, so there's other experiments that actually looked at this physics in systems that were not overcoupled. There, nothing really interesting happens because the interference is very, very, very weak. The nice thing about this optics implementation is there's effectively no other loss port, right? So all of the noise that's relevant can interfere. So that's something that I'm going to get into more, I guess, now in lecture 3. And the idea is, so at the end of the day, right, it's always the same thing that we're doing in this linearized theory, right? So at the end of the day, I'm ignoring the effects of this last term here, right? And one justification for that is, oh, well, this is enormous, right? This is what I wrote like this. I'm enhancing it by driving the cavity. That's really, really big. But then you could ask, well, wait a second. What if you try to do cavity cooling where the average number of photons in the cavity is order 1? Well, then this is the same as that, right? So then doesn't everything break down? And the answer is no, right? So the answer is that if I drive at the red sideband, this first term is basically just this beam splitter interaction, right? Because in my rotating frame, the mechanics in the cavity are resonant. So this term is resonant, has an amplitude little g if the number of photons is order 1. This term is non-resonant, right? This term, no matter what it doesn't change the number of photons. It changes the energy by plus minus mechanical frequency, right? Because it creates or destroys a phonon. Okay, so even if the average number of photons is really low, it's usually a good approximation to ignore this, because this term ends up being suppressed by that very, very small ratio. Okay, so your mean field approximation is much better than you would initially guess, because the corrections, right, not only are they missing this enhancement from the average photon number, they're highly non-resonant. That's a great question. So great that there might even be a slide. There we go. Yeah, so Patrice is hinting at this very, very beautiful experiment. And I would add like piece of theory. So this is a nice example where the experimentalist did some theory that the theorist thought at first was impossible, like that shouldn't work, but it works perfectly fine. So here's another way of using this kind of interference trick. Okay, this is not actually what the quantum noise spectral density looks like, but can I use interference to kill the emission noise, right? Can I do that without having to use a different kind of optomechanical coupling? So this is an experiment from John Teufel's group. And the idea is if I take my standard optomechanical system, standard coupling, cavity frequency depends on X, and I send in just the right amount of squeezed light in addition to this large coherent tone, well, then you also end up getting, if you tune things just right, a kind of Fano-like interference that completely suppresses the emission noise. So here's another case where even though your mechanical frequency is much smaller than the line width of the cavity, it's possible to cool to the ground state by using the right amount of squeezing. Okay, and it is a Fano interference. I don't know, I could tell you something probably crude. And is it an interference between the coherent and squeezed photons? There's some kind of interference that occurs in this system as well. It gives a Fano-like interference. Again,
this quantum noise spectral density is not just a density of states. You can cool to the ground state despite having a very, very low omega m over kappa. So the same approach absolutely works, and that's the language that John uses in his paper to describe the result. So that's an interesting question, right? So if you really tune, so in most systems, right, there's going to be some other imperfection that dominates why, at the end of the day, that interference isn't perfect. It's not exactly zero, it's something, and that will set your effective temperature. If that could actually be zero, right, then you might wonder that, well, anything will change zero from something that's not zero. So then you might ask, hey, what do higher order terms do, right? And so in either of these two cases, I wouldn't say use this general quantum noise approach. Use the specific kind of theory that applies to the particular coupling here. Now, what I'll tell you about actually next class, or next lecture, is a kind of Keldysh-based perturbation theory that you can do to systematically include higher order terms. And you're absolutely right. You could work out what would the correction be to the temperature you're able to cool to. And you would expect to get something non-zero. There's no reason to expect that, you know, with higher order terms, it still works in the same way.
Okay, last question, then coffee.
So they basically are able to measure the position fluctuations of the mechanical resonator by looking at the phase fluctuations of the output line. So as the mechanics moves, it modulates the cavity frequency, that changes that phase. So they're actually able to measure, right, so doing a kind of homodyne measurement. So by basically looking at the phase fluctuation spectral density of the light coming out, so the fluctuations of the phase quadrature, they can refer that back to the spectral density of the position fluctuations of the mechanical resonator. And what do they see? They see a Lorentzian centered at the mechanical frequency with some width that reflects the total damping of the mechanical resonator, both its intrinsic width and this extra damping that's coming from the optics. And then how do they actually get temperature? Well, they basically calculate the position variance just by integrating this spectral density, and then they use the equipartition theorem, right? So they're basically getting the mechanical temperature by looking at the size of x squared, right? So for all intents and purposes, from what they see a Lorentzian with some area. There's some variance of the motion. They're measuring the variance of the motion, okay? And then they're equating that to a thermal number of quanta. Okay? And then that basically, and now there's countless experiments showing that as a function of the strength of the optical power, as a function of the detuning, this quantity and this kind of measured temperature really follows the expectations from this kind of cooling theory that I've described. Okay? So by now, this is not even, you know, this is not even kind of like state-of-the-art sort of experiments. This is the first step in doing the really interesting experiment you want to do. You use this cooling physics to get close to the ground state. Then you do the experiment that you can submit to your fancy journal. The cooling is almost so routine now that, you know, it's buried in a supplemental information. You know, it works really, really well.
Okay, I guess we can thank Aashish for this very nice and lively lecture.